Welcome to AI Paper Podcasts, your shortcut to the latest and most exciting research in artificial intelligence.
Hey there.
In this deep dive, we're tackling a really fascinating paper from Tsinghua University, Embodied-R, Collaborative Framework for Activating Embodied Spatial Reasoning in Foundation Models via Reinforcement Learning.
Right, Embodied-R, CAGI-R. It's a pretty clever approach they've developed. It's all about boosting how well AI models can understand and reason about the world from a first-person view.
Like seeing through the eyes of a robot.
Exactly. Think like a robot navigating a room, but based purely on what it sees, and then figuring out what's where and what to do.
Okay, and for those of you needing the quick rundown, here's the gist. Embodied-R uses this smart combination, a big vision language model for seeing things.
The perception part.
And a smaller language model specifically for the reasoning. And it's all powered by reinforcement learning.
Yeah, and a key innovation is this reward system they built. It really pushes the model to think before it answers.
Leading to more logical responses, right?
Definitely. And get this trained on only 5,000 embodied video clips. This 3 billion parameter model performs incredibly well.
On par with giants like OpenAI's O1 and Gemini 2.5 Pro on these tough spatial reasoning tasks.
Even in new environments it hasn't seen before. Plus, it starts showing these emergent skills like systematic problem solving and integrating context over time.
So if you want to know how a relatively lean AI can punch way above its weight in understanding the world through its eyes, well, stick around.
So yeah, the core mission today is really to dissect how Embodied-R tackles this really tricky problem of embodied spatial reasoning.
How that collaborative framework actually works under the hood.
Right, and what makes it so effective, especially when you stack it up against, the current state of the art.
Okay, let's dive in then. The paper kicks things off by highlighting this fundamental challenge. Embodied spatial reasoning. It's not just about seeing objects, is it?
Not at all. It's about understanding their relationships in space, how they connect, and then figuring out what actions to take based on that understanding.
There's a real gap there.
Exactly. A crucial gap between just perception, what am I seeing, and true reasoning, what does it mean, and what should I do?
And current big AI models, while amazing at perception.
They are incredible at that, yeah. But their spatial reasoning, especially with video input, is still lagging behind quite a bit.
And video just adds layers of complexity compared to a single picture.
Oh, absolutely. For starters, good reasoning relies entirely on good perception. If the model messes up identifying what it sees,
then the reasoning is flawed from the start.
Built on shaky ground, exactly. Then you've got the whole dynamic aspect, objects moving, interacting over time. The model needs to track all that.
Keeping track of associations, extracting the important bits across many frames.
Right, to make sense of the whole sequence, like watching someone assemble furniture in a video, the AI needs to follow how pieces connect over time.
To grasp the final structure. Makes sense.
And these embodied videos, the first-person ones, they have their own quirks too.
Yeah.
Well, it's a continuous stream, right? And because the world changes smoothly frame to frame, there's often a ton of visual redundancy.
So lots of similar pictures one after another.
Exactly. Which makes it hard to just throw existing multimodal large language models at the problem. They can hit token limits fast with all that similar data.
And they might not generalize well to this specific first-person video type anyway.
Right. These big models weren't necessarily designed for this continuous redundant stream.
So the researchers looked at slow thinking, this idea that's worked well in LMs for things like math or coding.
Yeah, where the model carefully reasons through the steps before giving the answer. They wanted to bring that deliberate process to embodied video.
But how do you do that without needing a monstrously huge model, especially with long videos?
That's the tightrope walk, yeah.
Well,
Larger models are great for perception, but processing long videos with them gets computationally, expensive very quickly.
So this is where their Embodied-R framework really shines. And it's apparently inspired by how our own brains might work.
Kinda, yeah. Different brain regions for seeing, for basic spatial sense, and for more complex reasoning. So they design a collaborative approach.
Two main components.
Two main players, yes. First, a big vision language model. They used Qwen 2.5 VL72B instruct. It's good at the perception part, linking vision and language.
Okay, the singing part.
And second, a much smaller language model, Qwen 2.5 3B instruct. This one's job is the reasoning, the heavy lifting on the logic side.
And to handle that redundancy problem in the video feed.
Ah, yes, the Keyframe Extractor. This is a really neat part.
How does it work?
So Because adjacent frames are often super similar, it uses perspective transformation and an algorithm called ORB to figure out how much the view has actually changed between frames.
ORB, like feature matching.
Sort of, yeah. It calculates an overlap ratio. If the overlap drops below a certain point, meaning there's enough new information.
It flags that frame as a keyframe.
Exactly. It picks out the important snapshots.
Which must cut down on processing quite a bit.
Hugely. There are ablation studies where they tested the system with and without this part, showed like an 8.7% drop in training time and roughly a third off the inference time.
With minimal hit to accuracy.
Pretty much negligible accuracy difference.
Yeah.
So a big win for efficiency.
Okay, so we have these keyframes. How does the big VLM process them?
It goes through them sequentially to build up what they call an embodied semantic representation.
Sounds fancy.
It's basically a summary. For the very first frame, it identifies objects, their attributes, locations, the usual stuff.
Standard perception.
But for all the following keyframes, it gets smarter. It focuses specifically on the changes from the previous keyframe.
Ah, like delta encoding.
Kinda, yeah. It looks for inferred actions, changes in spatial relationships, new objects appearing, and anything directly relevant to the question being asked.
That seems much more efficient than reanalyzing everything each time.
Exactly. It avoids redundant processing and helps manage the input length, especially for longer videos. It aligns way better with how embodied experiences actually unfold.
Right. So the VLM generates these concise summaries.
These semantic representations.
And those get fed, along with the original question, Q, into the smaller LM.
Correct. And that's where the reinforcement learning kicks in to train that smaller LM.
Training it to do the actual spatial reasoning based on the VLM's perception summary and the question.
Right. The goal is to really nail that think then answer paradigm. You want logical reasoning steps leading consistently to the correct answer.
How did they train it?
They used a technique called GRPO, Group Relative Policy Optimization. It's known for being pretty computationally efficient for RL training.
Okay.
But the real secret sauce, I think, is their reward system. It's quite innovative.
Oh, more than just right answer gets a cookie.
Definitely more nuanced. They tackled a classic problem. Sometimes models get the right answer for the wrong reasons. Reward hacking.
Right, like guessing correctly on a multiple choice test without understanding why.
Exactly. So they designed 3 reward components. First, a simple format reward. Does the output look like think, answer?
Okay, encourages the structure.
Second, the accuracy reward. Does the final answer match the ground truth? Pretty standard.
Straightforward. But the third one, the logical consistency one.
This is the clever bit. When the model does get the answer right, they take the question and the model's reasoning steps the stuff inside think tags.
Yeah.
And feed only those into the original base LM, the one before RL training. Crucially, without the video frames.
Okay, so just the question and the reasoning chain.
Exactly. Then they check if that base model, given just the reasoning, comes up with the same final answer.
So if the reasoning itself is sound, the base model should also arrive at the same conclusion, even without seeing the video.
Precisely. It checks if the logic holds up independently. It penalizes cases where maybe flawed reasoning just accidentally led to the right output.
That's really smart. Did it make a difference?
A massive difference. They reported logical consistency jumping from around 46% to over 99% after adding this reward, evaluated using GPT-4o.
Wow, that's huge. So these 3 rewards format, accuracy, consistency, are weighted.
Yeah, weighted and adjusted across different training stages. Focus on format first, then accuracy, then really dialing in that logical consistency.
Okay, so they built this system, trained it carefully. How did it actually perform?
They put it through its paces, compared it against 17 other models, big names like GPT-4o, Gemini 1.5 Pro.
The proprietary giants.
Yep, plus state-of-the-art reasoning models like OpenAI's O1, Gemini 2.5 Pro, and various open-source VLMs.
A tough crowd.
Yeah.
And the results.
Pretty striking, actually. Embodied-R significantly outperformed the proprietary models and the SOTA reasoning ones.
Really? By how much?
By over 10% on average across their main benchmarks, Urban Video Bench and VSI Bench. And that includes both scenarios it was trained on and completely new ones.
That's a significant margin. It really highlights how tough embodied reasoning is for current models.
It does, and it suggests many models struggle to generalize well in these embodied contexts. It's strong validation for their collaborative VLM plus RL approach.
What about just using the big VLM on its own?
Well, they tested that too. The standalone Quinn 2.5 VL72B only got about 35% accuracy, Embodied-R, with the smaller LM doing the RL-trained reasoning, hit over 51%.
So decoupling perception and reasoning really paid off?
Clearly. They also tried just fine-tuning smaller models directly using supervised learning.
Did that work?
It helped, yeah, showed some improvement, but those models still lagged behind Embodied-R and, importantly, didn't really show that slow thinking pattern.
So speaking of slow thinking, did they find concrete evidence that Embodied-R was actually doing it?
They did. They analyzed its outputs and found it was good at reasoning about spatial relationships, like what's left of what.
Okay.
It also showed systematic analysis, breaking down problems, giving structured answers, kind of part-to-whole reasoning.
Logical organization.
Right, and it could integrate information across frames for a more complete picture, unlike some other models that might contradict themselves frame to frame. Plus, it stuck rigidly to that think, answer, answer format.
Consistent structure. And the Ablation Studies backed up the importance of each piece.
Absolutely. Confirmed the Keyframe Extractor saved time without hurting accuracy. Showed the VLM plus LM collaboration was key 1.5 times better than VLM alone.
And the RL training itself.
Huge impact. The LM's performance shot up after RL, proving it learned the reasoning task. Interestingly, they also found that the better the base text LM was at reasoning generally.
Before the RL.
Yeah, the better the final Embodied-R model performed. It suggests the framework benefits from both the VLM's good perception and the LM's inherent reasoning capacity, which is then further enhanced by the RL.
Fascinating. Did they look into anything else? Any other, research questions?
Yeah, a few interesting side points. RQ4 looked at response length.
Does longer thinking mean better answers, like in math?
Apparently not so much for embodied reasoning. Performance seemed to peak within an optimal range of reasoning length, suggesting overly long chains weren't necessarily better. Concise and focused might be key.
Interesting. What else?
RQ5, they tried applying RL directly to smaller vision language models instead of the separate small LM.
How'd that go?
Not as well. Performance was lower than using the separate LM in Embodied-R. The thinking is that the perceptual limits of those smaller integrated models held back the reasoning improvements.
So the decoupling was important even at smaller scales. And RQ7?
That was about generalization to really different out-of-distribution tasks, places like ego schema and MV bench.
And how did Embodied-R do there?
It showed stronger generalization than the models trained just with supervised fine-tuning. The RL training, that slow reasoning, seemed to help it adapt better.
Even for smaller models?
Yeah, suggesting the reasoning mechanism itself boosts generalization. On ego schema, Embodied-R actually got close to Gemini 2.5 Pro's performance, which is pretty impressive.
Okay, so wrapping things up, Embodied-R looked like a really compelling and efficient way to get better spatial reasoning into AI models for these embodied tasks.
Yeah, it's a smart combination leveraging the strengths of large perception models and smaller focused reasoning models tied together with RL that emphasizes logical consistency. Resource efficient is a good way to put it.
It feels like a significant step forward for tackling embodied intelligence, getting state-of-the-art results, showing slow thinking, better generalization.
It's definitely a noteworthy piece of work. And that logical consistency reward.
That seems crucial, right? For building trust in the AI's reasoning.
Absolutely. It addresses a really fundamental aspect of reliable AI. It's not just about the right answer, but the right way to get the answer.
This really opens up some exciting avenues, doesn't it? Thinking about scaling this, applying it to more complex real-world situations.
For sure. You can see the path towards more intelligent, more capable robots or virtual agents that can actually understand and navigate their environments more effectively.
For those of you listening who are deep in AI research, the paper itself is definitely worth digging into. Lots of detail on the experiments, ablations, all the nuances.
Yeah, a valuable resource if you're working on AI, robotics, spatial understanding, that whole intersection.
It leaves you thinking, though. What are the real implications of this collaborative approach for future robots or agents?
That's the big question, isn't it? How might this influence their design, their capabilities? As we get better at embedding this kind of slow thinking, what new possibilities emerge? Something definitely worth keeping an eye on.